Hello everyone, thanks for joining me for this presentation. As you can see on the screen, we're going to be talking about mapping with your drone or drone collected data. My name is David McKittrick. I'm Outreach and Training Manager for a company called Blue Marble Geographics. We're a software development company headquartered in the Northeast in the state of Maine. As I noted in my introductory slide, we're going to be talking a little bit about working with drone collected data. Ultimately, we're going to be generating some 3D data, 3D output files from simple drone collected images. Now, I'm actually going to do a simulated demonstration of that process and time permitting a little bit of kind of analysis of that data. But before we begin, we'll start again with some introductory content. Well, as you can see, a little simulation here on the left side is one of my colleagues sending his favorite toy up into the air. We're going to talk a little bit before we actually do our hands-on demonstration about some of the technical aspects of the process we're going to be going through, and specifically structure from motion, what exactly is involved in this. Now, ultimately, as I mentioned, we'll be generating a point cloud. Many of you, I'm sure, have used LiDAR data, are familiar with LiDAR data. What we're going to be generating is similar to LiDAR, but it's not LiDAR. There are distinctions, and we will be pointing out some of those when we get into the demonstration part, but we'll also talk a little bit about those variations. What's the difference between LiDAR and PHODAR? And as I said, most of our presentation today, most of the next half hour or so, we're going to be actually looking at a simulation of this process. I'm going to be using an application called Global Mapper. Many of you may be familiar with. I'm going to be using the latest release, Global Mapper Pro, to actually take a look at this technology. As I mentioned, we'll begin by talking a little bit about the underlying technology. What exactly is structure from motion? Well, it is important to note it is an image analysis process. Those of you familiar with LiDAR data, who have used LiDAR data, that data is collected using an active collection system, a laser-based system where you generate your 3D point cloud from real-time collected data. What we'll be using today, what we'll be generating today, is a result of image analysis based on overlapping images, similar to the way your eyes work when you look at an object on your desk from two slightly offset perspectives, your two eyes. You can start to see its three-dimensional characteristics. Now, you can take that principle and apply it from multiple directions. Ultimately, that's what's the underlying idea behind this idea for structure from motion. Looking at an object from multiple points of view allows you to reconstruct that in a three-dimensional context. In order for this process to work, the target area needs to have texture. It needs to have things that can be seen and identified and distinguished from other features around it. Areas with consistent solid colors will simply not work. A large body of water, snowfield, maybe even a large paved area where there's no distinction in terms of the visual characteristics. This process will not work for that type of application. So you need to have that texture. Obviously, your target area needs to have visible objects that would be detectable in your overlapping images. At least 60% overlap is what we'd suggest. As you'll see in the example we'll simulate a little bit later, we have a little bit more than that. We have significantly more overlap. Now, that's required for this process. Single side-by-side images will not work for this. You need to have the same object visible in multiple images. But apart from that, the technical or requirements are very basic. In captured images, which are identified in terms of their location in three-dimensional space. Recurring patterns of pixels in adjacent images are identified. I've kind of alluded to this already. This is how the process works. We're literally looking for features that we see in our target area that can be identified from multiple perspectives. And after that, it's just a simple process of triangulation to determine where those surfaces are in three-dimensional space, which ultimately will generate a point. That's obviously multiplied multiple times, and you generate a three-dimensional point cloud. You can incorporate, if necessary, ground control. I say if necessary, the structure of the target area can be recreated in arbitrary space, but obviously for geospatial precision, ground control will allow you to tie that into real-world coordinates, so your model will be geographically referenced or geographically more precise. So again, very high-level introduction to the underlying technology that we're going to be taking a look at in just a few minutes. we mentioned that we're going to be generating a point cloud, similar as I mentioned to LiDAR. What are the difference? Well, obviously the collection process and how it's generated are different. A little illustration on the left side of my screen, an aircraft flying over a target area, and you've got a drone capturing a single snapshot or an image. Obviously, we're dealing with active and passive data collection techniques. The passive being we need to take the output files, those images, those overlapping images, and process them in order to generate that data. So it is significantly different in that sense, both a value depending on your requirements. Just a quick side-by-side comparison here. You're looking at LiDAR detection and ranging. LiDAR on the left side, FODAR. I don't like the term, but a lot of people use it. Photogrammetric point cloud, or photogrammetrically generated point cloud on the right side. LiDAR obviously requires a little bit more planning. Yes, as a commercial UAV pilot, you still need to file a requisite flight plan and have, adhere to their local regulations. But it's a lot simpler to send up a drone than a fixed wing or a rotary aircraft. Obviously, the hardware for LiDAR, while it is coming down in price and certainly becoming more affordable and also smaller, it can be deployed on a drone. It's a lot cheaper to collect the necessary data when you're embarking on the photogrammetric process. More expensive typically, but again, that price point is coming down. It has come down significantly, but obviously with just a camera attached to your UAV, it's a lot less expensive. Output is critical as well in terms of how the data is collected. Obviously, with LiDAR, you're getting real-time data, typically clean, sharp, real-time point cloud. You can do a little cleanup to remove anomalies, but you end up with a resource that can be used for a lot of applications. Obviously, with FODAR, it requires a significant amount of processing, and we'll see the simulated process in just a few minutes. One of the significant differences when it comes to the actual point cloud itself is LiDAR, just given the nature of how that it's collected, can penetrate canopy. You will get a certain number of ground points even in areas of heavy foliage. When you're dealing with image analysis, that's not possible. If your target area is a forested area or an area with a lot of features that may obscure the ground, you're not going to get ground points. Maybe taking oblique images might be a solution, so you get a little bit of that oblique penetration under a canopy, for instance. But usually you're going to find you'll generate a great surface model, a DSM. Not so good if you've got a an area of heavy foliage. You're not going to get as many ground points, and we'll take a look at that when we look at our simulation just a little bit later. That said, let's take a look at structure from motion in action. So, quick introduction to the software. This is, as I mentioned at the start, Global Mapper. This is the latest version. We have just come up to release version 23. This is version 23 Pro, which includes a lot of LiDAR and point cloud processing tools, some of which we'll look at in this brief demonstration. Now, to give you a geographic perspective here, we're looking obviously at a target area. This is a little farm. I believe this is in central Vermont. We're just using this as an example. And the important part of this, for this area, we have drone collected images. You can see the flight path noted here. Each of these icons represents an individual frame. And we can load them into the application and see the location from a top-down perspective in two-dimensional space. We could also render this in 3D to see where they were in the air. We're not going to do that right now. If I use a selection tool here, I can just show you very quickly. I'll select one of the images. You'll notice it immediately shows me the approximate coverage area. Now, this will allow me to determine the appropriate overlap. And you can see in this case, we obviously have a lot of overlap. So each of these images is going to give us the necessary coverage or the necessary kind of perspective of our target area. Each of these can be also previewed. If I select an image, again with apologies from off screen, I'll just drag this into view, this window into view. You can see that image of this target area, and this is just a top-down image, obviously captured from the drone. If I select the next one, just use my cursor and grab the next one, you can see virtually the same image, but a slightly offset perspective. And as I mentioned in my brief introduction, that's the underlying premise behind how this works, these multiple perspectives. The tool itself that I'm going to be using is a tool called Pixels to Points. It is a part of the kind of the LiDAR suite of tools in Global Mapper Pro. A very, very powerful tool. Now, I have to say, I'm not actually going to go through the actual process because it'll take a little bit longer than the time we have available today, but I'm going to simulate how that process would work. I'm going to load up the image files that I have already loaded into the application, and you'll see they're all noted here with their corresponding coordinates as well as some additional information. Now, you see each has an elevation. It is a relative altitude based on where we assume local ground is, and a few other pieces of information about the images. If I have ground control points, I can add those as well. Ground control points will allow me to tie in identifiable features. Now, typically they would be targets perhaps that were laid on the ground to identify known coordinates. Again, I'm scrolling through here to find something identifiable in our images. Here we go. So as you can see, we've got obviously the buildings noted here, but if I had laid out a ground control point and I know the coordinates, I can identify that and obviously increase or improve the geographic precision of my output data. Not something I'm going to do in this case, but that would definitely be an option. We could also mask out areas that are not relevant, either by selecting a color. Maybe you've got distant parts of your images representing sky or water, as I mentioned at the start. Those are not going to be something that can be analyzed to determine their structure, so we can mask those. We can remove those from images as necessary. A few other settings here to determine output resolution, quality, etc. It will by default allow you to determine the three-dimensional characteristics based on the elevation of the drone itself. Now, obviously, if you've got ground control determining the actual location of a point, that no longer becomes relevant. But without ground control, you're basing the three-dimensional structure of your point cloud based on this X, Y, and Z derived from the drone, or the location of the drone. You can override that by defining a specific elevation of your initial target point where you take off from. Basically, the center point of that image, if you know the elevation of that one point, can be used as the basis for each of the elevations in the corresponding images or the corresponding output. You can also apply a post process, by the way, not something we're going to do today, but to three-dimensionally rectify your point cloud to make it positionally accurate after the fact as a post process. But again, this is where we initiate the process. Now, as for what we're going to be doing, the important thing is what we actually generate. We generate a point cloud. We're also, as a byproduct, going to get an ortho image, which is a gridded version of the point cloud. You're basically taking the points and transforming them into a raster layer, gridding them together like you would with a terrain layer. We're also going to generate a three-dimensional mesh or a 3D model. We'll take a look at that again in just a few minutes. Most of our work we'll do with the point cloud. We'll take a look at that point cloud, and again, time permitting, we'll do a little analysis of that point cloud, maybe transforming it into a DTM, maybe even generating some contours if we have time for that as well. But this is the basic tool that we would use to initiate this process. For the 148 images I have in this area, it will take about 45 minutes. Needless to say, I'm not going to go through that process right now. I'm going to close the dialog box and I'll show you the output files that would be generated. Okay, I'm going to begin by turning off the original images. We don't need those anymore. I can also turn off the reference base map. That served its function, give us a little bit of perspective, and we can take a look at the actual files. Again, we didn't go through the process, but had we done that, we would, as an output, have generated a point cloud. You'll notice the point cloud has inherited the colors that were captured from the images themselves. We also have an ortho image. I'll turn that one on. Now this will look the same, obviously. It's generated from the same source data, but this is a raster layer. What we're looking at now is a top-down layer that is a gridded version of the point cloud. Now this is not simply taking the original images and merging them together, or stitching them together. No, this is actually a new raster layer generated from the point cloud. We also generated a mesh as part of this process, or a three-dimensional model. Now from the top-down perspective, it does look just like the other two files. You're looking at, obviously, at the same target area, but really where this comes into its own is if I pop up a 3D view, and inevitably off screen I'll drag it into view just a little bit here, you're going to see a three-dimensional rendering of our target area, as you can see, a reconstruction of the three-dimensional characteristics. And again, it is worth noting that the source files that we're able to generate this are simply top-down, two-dimensional standard images taken from a regular camera, basically, but taken from a camera from multiple perspectives, and that's how it's able to reconstruct this. And this is a very good visual representation of what will be generated as part of the process. Now, the most useful component of the output is the point cloud. And the point cloud, as I mentioned, is similar to LiDAR, but it's not LiDAR. It has some significant structural differences. First thing to note is the spacing or resolution of the data. You can see I've zoomed in very closely here. I don't have my scale bar displayed, but had I my scale bar displayed, you'll notice that these points are very closely spaced. In fact, if we look at some of the underlying information about this output file, our metadata, we can see there's about 350, almost 360 points per square meter. Those of you who use LiDAR data will be used to maybe 3 or 4 points per square meter at most for some of the off-the-shelf point cloud data you may work with. Average spacing is 5 centimeters, so take an average over the extent of the point cloud. There's a lot of points in this area. If our intention is to generate a DTM, a digital terrain model, a surface model representing bare earth or ground, there's way more points than we need, and we don't need that degree of that level of resolution. It's a little bit overkill, and certainly the process is going to take significantly longer, and the file that will be generated will be much larger than we would need in a practical sense. So we can initiate a thinning process to remove points that we don't need, to initiate the kind of the removal of a little bit of the redundancy, if that is our objective. Now, obviously, maintaining the full resolution might be a requirement if you're interested in maybe extracting vector features, identifying buildings or other structures. Maybe maintaining that resolution will be important, but you can thin that. We're going to actually initiate that process in just a second. It is also worth noting that because we're dealing with LiDAR data, we can visualize this based on a number of inherent variables within the points. We're looking at the same data now, but we're looking at it represented by an elevation value. You can see the elevation values on my legend on the left-hand side. We can look at the same point cloud based on a classification. Now, in this case, unlike most of the LiDAR I'm sure you're used to dealing with, where you have ground points, you have maybe buildings and vegetation included in there. In this example, all of the points are unclassified. They don't come with a classification. So in order to apply value to this, we need to make sure we're using just the points that are relevant. And now specifically in this case, if our objective, once again, is to generate a DTM, a digital terrain model, we don't want to be using the points representing the building or the vegetation or trees or anything else that happens to be in this area. So we'll need to do a little reclassification, and we're going to do that in just a second as well. So just looking at our raw material here, there's a little bit of work needs to be done before we can do anything meaningful. For those of you who have not used LiDAR or point cloud data, I'm just popping up my 3D view once again, just to note that this is a three-dimensional point cloud. And you can see, it looks in many ways similar to what we saw with that mesh. That mesh that we looked at is actually a vector rendering of this area. But here we have individual points collectively looking at a reconstruction, but they are, if I get in close, still individual points. So as I mentioned, step one in our process, and we're going to assume that we want to generate a terrain layer, a DTM, a raster surface. This is now the raw material that will allow us to do this, but we need to go through a couple of processes. The first is thinning. I want to remove a little bit of the redundancy in my point cloud. And I'm not going to spend a lot of time going into the technical process, but let's say I want to thin this by maybe 5 times. In other words, remove 4 out of every 5 points to make a smaller point cloud. And I can retain, depending on my requirements, the minimum, maximum, etc. In other words, if I am interested specifically in ground, I'm likely going to want to target just the minimum points. Now, as a part of this process, I'm going to generate a new layer, and we can do a little back and forth comparison here to see the output. This will give us, let's just turn off the original. A point cloud, as you can see, is significantly thinner. It doesn't have as many points. More appropriate for what we're hoping to create, which is our DTM. Also notable is we still do not have classifications, but we can initiate a process whereby we analyze the structural characteristics of the point cloud at large to determine which points are likely to be ground, and that will give us the basis for the our DTM generation. Again, not dwelling on the details. I'm just going to quickly apply some settings here. Let me change my output resolution. We'll give ourselves a little bit of a threshold above and below ground. That should be fine. And all being well, when this process completes, it shouldn't take too long, we should see an additional color applied to the points in this area. And you can see quite clearly we have brown points now. To differentiate the brown from the non-brown, those unclassified points, I'm going to show a different display here, a cross-sectional view. Again, off screen, I'll drag this into view and you can see my cross-section a little bit flattened here, but you can see now where clearly we have identified points that are ground, ignoring those that are non-ground, buildings, vegetation in this case. That process is automated. That process is, again, is an underlying procedure to identify those structural characteristics. We're almost done. We're almost there. Our objective in this exercise was to generate a surface. We'll generate some contours as part of this as well, just to show that it actually works. But what we need to do as a final step is to transform this essentially vector point cloud, this three-dimensional point cloud data, into a raster surface. And for that, we initiate a process called gridding. That gridding creates pixels from your vector data, from your points. It could be LiDAR, or in our case, it's a photogrammetrically generated point cloud. Very quickly here, I'm just going to go through confirming the layer that we're going to be working with here, the only layer that's currently visible. And we can determine the output resolution, a few other things in here. We're creating a DTM, so we're going to call it DTM. We're going to create a binned version. In other words, we're going to do a sample based on a defined linear unit. And within each of those, we're going to look for the minimum value. Once again, because we're generating a DTM, we want to make sure the lowest point within our pixel, or what will be our pixel, is the one that's factored to determine our elevation model. Everything else here should be fine. We'll click OK, and shouldn't take long. Once again, with apologies, this is a little bit of a rushed demonstration, but we want to make sure we're using this time to its best effect here. I'm going to turn off the point cloud, and hopefully we can see our surface model. I just realized I did not remove the non-ground points. Let me go back and do that one more time so we can do a little bit of filtering here, because I didn't address the fact that the buildings were still part of my point cloud. Let me initiate that one more time with apologies here. Again, we're just going to remove all but my ground points. Those unclassified points will not be factored into the output model. Everything else should be the same as it was before. I'll just rename this DTM2 just to differentiate it, and we'll click OK. Again, shouldn't take long, and we'll get a version of what we just generated that is just the ground points, effectively interpolating where there were unclassified points before, and you'll see that buildings have been removed in this case. I'm going to change one of my settings here to bring the vertical exaggeration down just a little bit. And there, that's flattened it nicely. So we now have a raster surface representing not the surface, the canopy surface, the building surface, but the ground. We've isolated ground. Some of the things that we can do with this, I mentioned, we're introducing this, maybe some contour generation. Again, to verify that this is actually a surface that we can use, we initiate the process of generating some contour lines. Maybe I want my contours to be 1 meter contour lines. A few other options in here to identify local peaks and depressions. I'm not going to initiate that in this example. We have options to remove local anomalies. Maybe there are contours that are just derived from some local high points. Maybe we do not want to keep those. I'll put a threshold of 20 meters in here, and we'll click OK. And what we generate are vector line features, again derived from the surface model, which ultimately was derived from the point cloud, which, if you go back far enough, was derived from some simple drone collected images. And you can see those contours clearly noted in here. We could spend the next 2 hours going through some of the other processes that we could initiate now for volume calculation, perhaps line of sight or view shed analysis or watershed delineation within this surface area. But I wanted to give you an illustration just at the end here, how we can use these drone collected images, these images that were simply top-down, two-dimensional, collected images of our target area, run run through a process to identify their three-dimensional structure, their three-dimensional characteristics, and ultimately create a surface that allows us to initiate multiple terrain analysis procedures. This was a very rushed simulation, I understand that, with apologies. If you have questions, I'm going to be here for questions if you want to ask questions. Also, I'm going to provide an email address. If you're maybe watching the recording of this and you want to follow up, I'll give you an email address in just a second that you can ask me additional questions as necessary. Thank you for attending, folks. Thank you for taking the time to sit and on the presentation. Hopefully you found it useful. And we went a little fast there, going through some of those procedures without dwelling on too many of the technical details. But hopefully you got the gist of this idea of using a drone as a data collection tool for your geospatial work, specifically your 3D geospatial work. As noted, if you have questions, you may be watching the recording of this presentation, email address you see on the screen, geohelp@bluemarblegeo.com, is our tech group here at Blue Marble Geographics. The folks in the tech team would be more than happy to answer any questions that you have. You may want to mention that you attended the presentation or are watching the recording of the presentation so they can answer your questions in the appropriate context. If you want to try Global Mapper for yourself, there is a URL again on the screen here, bluemarblegeo.com/globalmapper. You can download the software. There's a free 14-day trial. If you're using a drone, if you're collecting images, you can go through the process that I went through to see how that works with your data. And again, if you have questions during that trial process, don't hesitate to get in touch with us. Once again, thank you folks for giving me the opportunity to speak and for attending the presentation. Thank you very much.